Great. Okay, so today I'll be giving you an update on progress in quantized inertia. And yeah, let's move that. So I'll explain what inertia means, what the old model was, the new model I'm suggesting, quantized inertia. I'll discuss various bits of evidence for it, astronomical and lab evidence as well. And then, as Boris said, I'll talk about some applications. So I've chosen to show this object, this circular galaxy, which is called Hoag's object, because it's probably the most beautiful illustration of quantized inertia. And hopefully by the end of the talk, you'll understand why. But it's a very interesting galaxy. It's got a core in the center here and a ring of material outside. And you can actually see it. It's in the constellation Serpens Caput, which is in the northern hemisphere. And you can see it if you've got a 20-inch telescope or more. So I think your society will be able to look at that. Okay, so I don't really need to go through my background again because Boris has already done that. Just to point out my books, 4 books here. Okay. So what is inertia or inertial mass? Well, a long time ago, of course, Aristotle thought objects tend to stay at rest until you force them to go. And that's kind of the obvious first impression people have, because most things are subject to friction. So he didn't believe it when Aristarchus proposed his heliocentric theory, saying that all the planets rotate around the sun, as shown in this diagram, sun in the center, the planets orbiting, because he thought that things would fall off the planet in its motion if they were if they tended to stay at rest, like as shown here. And in fact, the word inertia is Latin for laziness. This was Aristotle's thought, that things tend to stay at rest. But it was in the late Roman Empire that Philoponus in 550 AD first realized that the actual rule was that things tend to keep going at constant speed unless you stop them, which is closer to our understanding of inertia. And he was in trouble at the time for not agreeing with the dominant religious ideas. So he was cancelled, and it took over 1,000 years for Galileo to rediscover his work in about 1600. And so he was the first to write at length to say that inertia is a tendency of objects to keep going at constant speed unless they're forced to stop. So an illustration is this ladder on top of the lorry here in the animation. The lorry hits a car and stops, but the ladder continues because it has inertial mass. And the great thing about this was it allowed Galileo to accept the heliocentric theory that the Earth revolves around the sun, because he realized that things would quite happily follow the Earth in its orbit and wouldn't fall off the planet if it was moving. So people have now an innate understanding of inertia. I mean, this is a plot from the Raiders of the Lost Ark, where Indiana Jones is running from the big ball right at the beginning. And Indiana Jones obviously has an intuitive understanding of inertial mass because he understands that the ball is going to continue running, continue moving. But inertia has never been understood. People have this assumption for it, that things keep going in a straight line. But the question is, why do they do that? And I proposed the first model to try to explain why that is the case. But because some of my background is in ocean waves, I'm going to try and explain it using those waves with an analogy here. So imagine you've got a speedboat on a lake. So here's the speedboat in the center, and it's moving to the right. It's accelerating to the right. It'll excite waves on the lake, so you get lots of waves in front of it, which will hit it and push it back against its acceleration. But behind the boat, there'll be fewer waves, because waves from this part of the lake will not be able to catch up with the boat. And also, the boat's going pretty quick, so the waves won't be fast enough to catch it. In physics, we call an idea like that a horizon. So I've put this black black line here to represent the horizon. This means that information from waves behind this area will never catch up to the boat. And what this means is that more waves will hit the boat in front than will hit it from behind, so it'll tend to be pushed back. So this is very much like the inertial mass we know. And it's quite a close analogy, but it's not a perfect one. But there is a caveat to it. What we could do is get extremely wise and avoid having inertia, which always absorbs energy, reduces the energy we have in movement. So if we were very clever, we would accelerate very slowly, because the slower you go, the less energy you put into the waves and the longer wavelength they get. And if the energy you put in is so low that the waves are longer than the lake, then they can't form on the lake, because the lake is a bounded area. So you would get a flat lake then. So you would be accelerating with a flat lake. There'd be no waves pushing from both sides of the boat, and there'd be no pushback, no inertial mass. So in that way, you'd be able to travel far more efficiently with less energy. So in terms of waves, this is a whole concept of quantized inertia. But we have to, instead of using water waves, we have to think about quantum waves instead, but it's essentially the same. So I'm considering, in this plot, I've got an object, this black dot in the center, which is accelerating to the right. And according to quantum mechanics, it was discovered in 1976 by Unruh, well, Fulling Davies and Unruh, that every time you accelerate, you see a thermal bath of hot radiation surrounding you. You see quantum waves surrounding you. And it's called Unruh radiation now. And it has recently been seen. When I first started proposing quantized inertia, it had not been seen, but it now has. It was seen in 2021 by Lynch et al. So the paper is referenced here. And he actually emailed me in some excitement to tell me that he'd seen it. He found it in CERN data, where they fired positrons into a silicon crystal and it decelerated very rapidly and emitted radiation which looked just like Unruh radiation. So it has now been seen. So this object will see Unruh radiation, and I've tried to show that with this red coloring. But the object is always also accelerating to the right, so it'll see a horizon behind it. Information from this black area won't be able to catch up with it. So there'll be a horizon. So the main new thing about quantized inertia is that there'll be a damping of the waves, these quantum waves, by the horizon. So there'll be fewer of them on this side of the object. So there'll be lots of waves, quantum waves, pushing it from that side, but fewer pushing it from that side. So it'll be pushed back. And I managed to show in a paper in 2013 that this looks just like inertial mass, mathematically. But it's not quite the same. There's a very tiny difference. And it's this tiny difference that enables quantized inertia to fix most of the problems in astrophysics. Because we're in something called the observable universe. So this is supposed to represent the observable universe, a part of it we can see. If you have a rocket accelerating rapidly, so shown here, it'll see short Unruh waves. So I've shown those with the red waves. And they'll be in front of it and they'll push it back. So this rocket will have inertial mass. But if the rocket has an extremely low acceleration, then the Unruh waves will be very long. And if it's low enough, they'll be bigger than the size of the cosmos. So they will be, in principle, unobservable. So that means they can't be seen. And if something can't be seen, then I'm assuming it doesn't exist. If it can't be detected, it doesn't exist. So in this way, you can derive this formula for the modified inertial mass. So the new inertial mass of the object is given by the original one times this factor, 1 minus 2 times the speed of light squared, divided by the acceleration of the object times the cosmic diameter, this capital theta here. So this So there are two ways to make this effect important or observable. The first way is to have extremely low acceleration. So if a is very small, then this term becomes larger. So you get 1 minus a large value. So this term reduces, so you get a lesser inertial mass. And I'll show you in a minute that this explains galaxy rotation when a is small. The other way to reduce or affect inertial mass is to make the universe or the cavity size very small. And I'll show you towards the end of the talk that if you can do this, put something in a cavity, then you can affect the inertial mass and produce propellantless propulsion. Okay, so this part of the theory I published in 2007 in this journal here. So this is the Andromeda Galaxy. So in the center, it behaves quite normally. It follows Newton's laws. But at the edge, stars tend to orbit far too fast for Newton, so that the centrifugal force that they see pushing them out will be extremely large. And it turns out that it's much larger than the gravity that's pulling them back in. So astronomers have invented dark matter, and they add dark matter to the galaxy to help bind it together. But they need to add many times more of a mass of dark matter than they can see in the galaxy. So it's a huge addition. And also they've been looking for 40 years and they haven't found it yet in the laboratories. So I'm not very fond of dark matter. But it turns out that if you use quantized inertia, what it does is the stars at the edge of the galaxy here have such a low acceleration that their inertial mass reduces following this equation. If their inertial mass reduces, their centrifugal force also reduces, and it turns out it reduces by exactly the amount needed so that the centrifugal force balances the gravity pulling inwards. So the stars can happily orbit around the edge of the galaxy, not fly off into space, and not collapse into the center. It's perfect. The fit is absolutely perfect, and it does it without adjustment. It's quite simple. And the only information you need is the visible mass of the galaxy, the speed of light, and the Hubble scale, the size of the cosmos. So I published that in this paper here in 2017. But it's even better than that. The proof gets even better than that. If you look at a galaxy and you look at the center, the acceleration is high. So the under waves are short, and I've shown that down here with these short waves. As you move out to higher radii, the accelerations reduce and the waves get longer. But it turns out that at the exact radius that the acceleration is such that the under waves are the size of the cosmos, the size we know its size, as soon as you get to that radius, that is when the behavior of the galaxy changes. The behavior of the stars changes. So this is a direct proof that it has to be under waves that are causing this effect and quantized inertia. Okay, so what are the consequences of this? Well, the first thing the theory predicts is a minimum acceleration. So starting again from this formula and using Newton's second law, so F equals ma, where this is the inertial mass, and the gravity law as well, so this is the force. If you substitute this formula here for the inertial mass, you get this formula here, that the acceleration is equal to the usual gravitational one, but plus a new term, which wasn't there before. So this is 2 times the speed of light squared divided by the cosmic scale. And it turns out this value is 2 times 10 to the minus 10 meters per second, which is the acceleration that is usually referred to as cosmic acceleration. It's the acceleration of the edge of the universe that has been observed and attributed to dark energy. So what this means is that there's always a minimum acceleration in nature, no matter what the gravitational attraction is, even if this is 0 or close to 0. there's this extra term that comes in. So you might notice that this contradicts Newton's first law, which says that things tend to travel at constant speed. Tend to travel at constant speed. Well, with quantized inertia, there is no constant speed allowed. You have to have a small acceleration, but I can perhaps be excused because it's only a very slight change. The acceleration you need is only about 10 to the minus 10. That's very small. So only snails might be affected by this. Things that move very, very slowly. So I've shown that the theory predicts galaxies very well, but the problem there is that astronomers can say, but we can model them with dark matter as well. We can just add dark matter where we want and make it work. So I needed to find an observation that can't be explained by dark matter. So I looked at wide binaries. So these are stars that are more than 7,000 AU apart, but still mutually bound. They're very far apart. And sure enough, they orbit each other faster than expected, just like galaxies, stars at the edge of galaxies. One example of a wide binary, well, two of them actually, are Alcor and Mizar in Ursa Major. These are actually both double stars, and they're visible as well. The great thing about wide binaries is that you can't add dark matter to explain them. You can't pack dark matter in between them to hold them together, because in order to explain galaxies, you have to put the dark matter around the edge of the galaxy. So you have to give it new physics to make it repel itself. So if you do that, you can't then pack it into a small region of space because it's contradictory. So wide binaries are the perfect test for QI. So I got my postdoc at the time, Dr. Jesus Lucio, to model this, and we put two stars next to each other as wide binaries. And then we saw, we modeled them with three different kinds of physics. So Newton, which is shown by the blue lines, then Mond, which is arrival theory, but it needs an adjustable parameter, and then quantized inertia in red to see which theory would bind the wide binaries together, because we know they're bound in the observations, but we'll see which theory predicts that. So if we run the model, you can see that Newton and Mond both have the stars diverging from each other and spinning off into outer space, and only quantized inertia keeps them bound. So this is nice proof, and we published this in a paper in 2019. Okay. So not content with that, I've been looking for even smaller, similar systems. So, and I read a paper last year by Pearson and McCulloch, and they've been looking at the Orion, the trapezium open cluster in the Orion Nebula, which is shown here, with the James Webb Space Telescope, and they've found 42 pairs of what they call Jupiter mass binary objects, or jumbos for short. They're not bound to any stars, these things. They're just orbiting around each other in binary form, with separations up to about 400 AU and masses close to, well, from 1 to 13 solar masses. So as soon as I saw this, I thought, well, perhaps these objects are in an area where there's very little gravitational acceleration. So maybe they will show the minimum acceleration that quantized inertia predicts. And it turns out that they do. So what I did was I plotted on this graph here the separation of each pair within the binary. So from about 50 AUs up to about 400. And then their mutual acceleration up here. And you can probably see that as the separation increases, the acceleration reduces, as you'd expect, but it's it asymptotes to the QI minimum acceleration of 2 times 10 to the minus 10. Like that, it's quite clear that there's a slowing down, and so I think this is good evidence that there's this minimum acceleration that objects try not to go below. But when I write papers, I like to predict something that hasn't been seen yet. So I predicted that these very widely separated binary objects will orbit far faster, well, a little bit faster than expected, because they've lost inertial mass. So they're able to orbit faster without the centrifugal force pushing them away. And so the bottom graph here shows the speed boost that I predict for these. So for the wider separated ones, it's about 70 meters per second, which should be able to be seen by the HARPS telescope. It's an exoplanet finder telescope. It can determine how the Doppler shift and the speed of systems like this. Okay, so looking back at this same formula for the inertial mass, you may remember that I said that if you were able to reduce the cosmic scale, then what would happen is the inertial mass would reduce, and the centrifugal force would also be reduced. So one way to reduce this universe size is to look into the past, because in the past the universe was smaller, certainly informationally. So what I did was I looked at some data from Genzel et al., 2017 Nature, where they've looked at galaxies that are very far away, very high redshift, and so they exist in a universe that was much smaller. So I've plotted these on this graph with these dots. So the x-axis shows the observed acceleration, and the y-axis shows the predicted one from quantized inertia. And the prediction is of the theory that as you go to higher redshift, the acceleration should increase, because the inertial mass should be lower, so the centrifugal force should be lower, so they can afford to spin faster without falling apart or flying apart. And you can see that this is in fact the case. So as you go to higher redshift, the acceleration increases. For perfect agreement, they should all lie on this line, but they're not far off it, except this one, which is a bit of an anomaly. So I published all this in a paper in 2017. And more recently, and this is brand new, I've seen some data on even earlier objects. So these are called little red dot proto-galaxies. So there's a picture of one here. So it's pretty redshifted. And this was discovered by the James Webb Space Telescope in 2024. And there are over 300 of them. The redshift of about Z is 5. So very early in the universe's lifetime, about 1 billion years after the Big Bang. They're extremely small, and they show a very broad emission line. So the way they determine the speed of the stars in them is by looking at the Doppler shift of the stars on one side against the other, because some of the stars are moving away, some are moving towards us. So the Doppler shift is different on both sides, and the greater it is, the faster the speed. So they found that the rotation speed of these things is about 1,500 kilometers per second, which is much greater than galaxies these days. Galaxies these days have about speeds of about 200 kilometers per second. So what does QI predict for their speed? Well, the formula is shown here. So that's the speed of the edge stars. It's determined by the gravitational constant times the mass of the system of the galaxy, speed of light squared divided by the cosmic scale, which I've had to modify because we're looking at the universe in the past. So the the cosmic scale is less. And you can assume a few of the things as well. But basically, putting in values, QI predicts that the speed of them should be about 1,300 kilometers per second, which is in agreement with what's seen. So I'm hoping to write a paper about this fairly soon. Okay. So there's also another big problem in astrophysics called the flatness problem. The problem is that when you look at the cosmos as a whole, its potential energy equals its kinetic energy. And another way of saying it is that the cosmos is flat or just closed. This means it's got just enough kinetic energy to reach a peak before falling back and collapsing. So why should this be? It looks very much with the current model to be a coincidence of the current epoch. So it seems that potential energy equals kinetic energy just at the current epoch, which seems extremely unlikely. And this was pointed out in a paper by Unziger in 2008. But this can actually be predicted by quantized inertia, because in the theory, in any volume, the acceleration has to be high enough so that the under wave seen by the objects is smaller than the cosmos. So you can write this the following ways. You can say that the gravitational acceleration has to be at least this size. This must produce an acceleration of at least this size, where this is the 2 times 10 to the minus 10 value. And then the cosmic diameter is just 2 times the cosmic radius, which is shown here. So what you get is that the potential energy, g mass over radius, is equal to the kinetic energy, which is c squared. So you may not recognize this, but there should be an m on this side and m on this side, but they cancel out. So this gets rid of the need for inflation in the early universe, because one of the ways astronomers try to explain flatness is by proposing that the early universe inflated very fast. This was done by Alan Guth. And it early gets rid of the need for early fine-tuning or assuming a special era now, because this formula is true for all times, for all epochs. And also, the same thing helps us get rid of the gravitational constant. So big G has always been part of physics, but it turns out that with quantized inertia, you don't need it, because, as I said before, that you can derive this equation and rearrange it in terms of G. So G is simply the speed of light squared times the cosmic diameter divided by 2 times mass of the universe. And it's been known for many years that this formula looks true, because if you put the values in, you get a pretty good agreement. But quantized inertia gives us a way to say why it's true for the first time. And the exciting thing about this is that it enables us in a way to unpack the gravitational constant into these values. So that means we might be able to control it. For example, what would happen if you changed the cavity size, which is represented by this value, or the speed of light? Would G be different? And in fact, it is known that G varies. Several experiments have shown that it varies. So this is interesting, and it might be applicable in some way. Okay, and then very recently I've been looking at the interstellar comet 3I Atlas. So this was a comet discovered by the Atlas telescope in Chile in July 2025. It's called 3I Atlas because it's the third interstellar comet. So they found Oumuamua and Borisov before, and this is the third one. And this is an image, I think this is the best image of it that was taken. It was taken in New Mexico by a Celestron Edge telescope by Satoru Murata. And you can see the normal tail here, and there's also an anti-tail. It's a very large one, as I'll show in a minute. It came closest to the sun in October, the distance of just over an AU, with a huge speed of 68 kilometers per second, which is why they assume that it's an interstellar comet, because it has so much kinetic energy that it's going to escape from the solar system. So goes the standard theory. But Avi Loeb has pointed out a few anomalies. So he's shown on the top right. He pointed out that its trajectory is unusually within 5 degrees of the ecliptic plane. So as I'm sure all know, if the sun is here, all the planets orbit in a plane. And so does this comet. It orbits in the same plane, which implies that it's actually part of the solar system. Well, it implies to me that it's part of the solar system because it's part of the same condensed cloud that the planets are formed from. But of course, it can't be part of the solar system because it's moving too fast, 68 kilometers per second. The second anomaly that I'll pick out is that, sorry, I should say too, its nucleus is 1,000 times the mass of Borisov, which was the second interstellar comet, and it's 1,000,000 times the size of the mass of Oumuamua, which was the first interstellar comet. So it's absolutely huge. And Avi Loeb pointed out that it's very unlikely that objects of this size would be rolling around in deep space, and that there would be such a wide range of masses in interstellar comets. And also he pointed out that at perihelion, it showed quite a few anomalies in its trajectory, which is very, very interesting to me. Of course, Avi Loeb was very interested in suggesting that this was an alien object, but I think there might be another explanation using QI, because I've been modeling the orbit of it. So what I've done is I've initialized a Fortran model of the orbit with NASA Horizons data. You can get very accurate data on trajectories and positions and speeds from NASA using their Horizons website. And I started it off at close to perihelion with this accurate data, and I ran it with Newton, and I ran it with the quantized inertia physics. And what happened was that it behaved quite normally at first, but then as it moved away from the sun and into a region where the acceleration is so low, two things happened. First, it lost its inertial mass, so it was attracted more by the sun, back towards the sun. And the second, as it lost its inertial mass, in order to conserve momentum, it has to speed up a little bit. So these two effects are complementary. It's quite an interesting problem. You need some quite good numerics to model it properly. But essentially what happened is that instead of zooming off into outer space, it slowed down and came to a very close stop at about 2000 AU, and then stayed out there for a very long time, and then zoomed back in, zoomed past the sun, and then went out the other way and did the same thing. So what this implies is that this interstellar comet is not actually interstellar. It's actually part of the solar system. It's part of the planets, and this explains why. This helps to explain why it's coming in on a plane of the ecliptic, because it came from the same mass that formed all the planets, and also it explains how it can be so massive as well, because it's part of the solar system. And so it's not that we're going to have to wait for close to 1 million years to test this. Quantized inertia predicts that it should be showing some trajectory anomalies fairly soon, within a few years. So that can be tested. But this is very different to the Newtonian, what Newton or general relativity would say. So the Fortran model I wrote to model this, I put on my Patreon site, which is here. So it's available there, although you do have to pay to join. But you can run it yourself, and you can see for yourself what happens, and you can run different scenarios as well. And so far it's been corroborated by two people, one of whom is from this from your astronomy society, actually. They've both run the model. Okay, so this might be of interest to planetary defense as well, because we need to be able to model these things quite accurately. And there seems to be a subtle difference here between Newton and quantized inertia in these orbits. Okay, so more generally, what I'm trying for here is, in a broader context, I'm trying for a campaign for real physics, if you like. With general relativity, that's you can test the effect of the model, which is curved spacetime, but you can't test the mechanism of it to confirm that this is actually being caused by curved spacetime and not something else. And plus, also, general relativity gets galaxies, predicts them wrongly. But with QI, you can test the effect and the mechanism. So it's more intuitive or more visceral, if you want. When Lucy throws a snowball at Charlie Brown, you can test the effect, because you can see Charlie Brown falling over, and you can also see what's causing it. It's the motion of the snowball. Well, quantized inertia is more like that. It's very difficult to determine whether space is actually bent, except by passing an object through that space, which then bends. But you don't know if it's the actual bent space or some other effect causing it. With the quantized inertia explanation using the quantum background, you can test it because you can measure things as they curve, but you can also then measure the intensity of the quantum background at different points in space, and so you can see what the effect might be. And it also means it's useful for technology as well, because it's more tractable, and it predicts galaxies correctly as well. Okay, so hopefully I've presented enough evidence for quantized inertia. I'm now going to look at applications to thrust. So imagine you've got an object here, this black circle, which is accelerated hugely, so it's spun at a very fast rate. So because it's accelerating, it will see Unruh waves, shown by these red arrows. And the faster you spin the object, the greater the acceleration, the shorter the Unruh waves will be. Normally, for the accelerations we have on Earth, they're about a light year's length. But if you spin up to about 10 to the 18 meters per second, they'll be less than a meter in length. And that means that you might be able to start damping the Unruh waves with metal plates. So you see I've put a metal plate above this spinning object. So it will see Unruh waves from below pushing it, but it won't see any Unruh waves from above. So it'll tend to move up. So this might be a new way to move things, even launch them. So I suggested that in a paper here, and then DARPA contacted me, and I applied and was awarded 1.3 million to try to demonstrate this in the lab. And the first thought that we had was to look at the M drive and things like that. So this is something that was invented by Roger Scheuer, who's shown here as a British engineer. And he found that if you put microwaves into a conical resonating cavity, copper cavity, they tended to move towards a narrow end. And in thinking about this, I realized I could explain it with quantized inertia. Because if you have a conical cavity like this and you put microwaves into it, it makes the electrons and also the photons in there, the microwave photons, shuttle from one end to the other. And every time an electron or a microwave photon moves towards a wide end, more Unruh waves are available because it's a wider end. So there are more wavelengths existing at that end. So inertial mass is more efficient at this end. But every time they go to the narrow end, there are fewer Unruh waves. So inertial mass is less efficient. So the upshot of this is that you get a slow transfer of inertial mass towards this end. And in order to conserve momentum, the system has to move towards a narrow end. And I found out that just from this equation and its consequences, I could predict the thrusts that Scheuer saw. So I published that in this paper. And I could even predict the changes that occurred when dielectrics were put at the wide end and the narrow end to change the speed of light, which was interesting. And then two engineers from California, Becker and Batt, 2018, suggested to me that a better way to do a similar thing would be to use capacitors. So this central picture shows a capacitor, two plates, and electrons pass from the cathode to the anode at an incredibly high acceleration, about 10 to the 19 or so meters per second. So they produce underwaves that are very short, so about the size of the cavity, and this means that underwaves are damped between the plates. The acceleration is very large, so the underwaves are quite intense, but then they're damped. So this means that the electrons are losing their inertial mass as they cross, and in order to conserve momentum, the system itself has to move to compensate to the anode, and that's in fact what we tried. So Becker and Batt did an experiment, and I've shown the results here. So the x-axis shows the separation between the plates, so it's about 80 micron here, down to about 10 micron here on the left, and the force gets up to about 6 millinewtons, and you can see that the force that they saw increases exponentially as you go to a narrower separation. So the black diamonds are the observations, and the theory predicts the squares, the open squares, and it agrees very well with the data. So it predicts the thrust perfectly, and I published that on ResearchGate in this paper here. So this is an easier method to generate thrust than the M drive, and again, it doesn't need any fuel, just energy. So since then, I've liaised with quite a few groups to do this, to try this in different labs. So Becker and Batt were the first in 2018, and they observed a thrust of 6 millinewtons, and I predicted about 6. Then an American company called Ivo in Virginia, they tried it in a vacuum because some people said it might be ion drift or something. So they tried it in a vacuum, and they saw 6 millinewtons again, and I predicted 5.25. And then we tried it in Plymouth as well. I tried it with an engineer, Richard Arundel, and in 2022, and we got agreement as well. Although our thrust was smaller, it was predicted to be smaller. An Italian group tried it as well, and the theory agreed with that. There was a Charles Bueller as well of Exodus Technologies tried it, and there was a group in California. So several groups have now tried it and seen good results. And then Ivo, who did the vacuum test, they launched a CubeSat with a capacitor quantum drive on it in March. So they used a SpaceX launch, Falcon 9, I think it was, and it was a Rogue Space Systems CubeSat that they used. This is Richard Mansell, their chief executive. And yeah, so that's been up there for a few months. So what I've done here is this is sort of hot off the press, so I hope there are no errors here, but what I've done is I've compared the Ivo sats, this one's fall, with a satellite that is almost identical. So 3 months ago, it was 506 kilometers height. And very recently, it was about 501.4 kilometers height. So it fell by about 4.88 kilometers. Yeah. So, and then I've chosen a satellite that was launched on the same rocket and has an identical shape, or a very similar shape. This one, NORAD ID 63220, and it started off at 504 in September and ended up at 499.5. So what that means is that the IVOSat fell 600 meters less over 3 months. So it means 6.6 meters up per day. So compared to the control, it was thrusting 6.6 meters up per day. And you can work out, so I have to be careful because they did have a problem with the hardware and software on the satellite that meant that their burn time was limited. They weren't able to thrust as much as they wanted to. So what I've tried to do here is estimate how much they did actually manage to burn it, burn the engine or the quantum drive. And if you take that into account, it predicts that the change of height should be about 10 meters or so burn. And then if they fire it every other day, which is, I was monitoring them for some time, and I think that's roughly what they did, or maybe every 3 days or something like that, then the change of height should be about 5 meters, which is not far from what they were seeing, about 6.6 meters. So yeah, what I did was I asked the Richard Mansell what I was able to tell you about the tests, and he said this. So feel free to tell them that this was Rogue and Ivo's first time to test hardware and software in space, and there seem to be some issues with the testing hardware. As you know, it isn't the drives themselves that were acting up, but something with the command and control mechanism. Lord willing, there'll be another space test. So hopefully there will be another space test, but I think the results look encouraging given this. So what's next? Well, space tests are incredibly hard because you can't tell, you can't get up to the satellite and check out the engineering. The best test would be a lab test that would enable us to look at what's going on, see if there's a problem, and then slowly enhance the thrust, and then levitate and launch it. Though I'd like to try this, and QI suggests ways to enhance the thrust. For example, the one way to do it would be to reduce the separation between the plates, but that's problematic because then you need a much stronger dielectric. But there are other ways that I've thought of to enhance the thrust, and several funders are considering backing this at the moment. And further into the future, what this means is that the normal problem with interstellar travel is that in order to get up to the speeds needed to get to the nearest star in a human lifetime, you need huge amounts of fuel, and then you need even more fuel to carry the fuel that you've got. That's a big problem in interstellar travel. So, but this kind of propellant is, this kind of propulsion is propellantless. It doesn't require any fuel. It just requires energy. So it enables you to travel long distances in a much shorter time. For example, with this system, we could send a probe of 100 kilograms to the Oort cloud in 1 year. With rockets, it would take 500 years. And I also predict that we can get to Proxima Centauri in about 10 or 15 years. And with rockets, it would take 70,000 years. So I have done some design work on a possible probe to Proxima, and it's shown here. And thanks to Kelvin Long and Richard Arundel for input on the design and the costs, this is effectively a column of stacked capacitors along here, which will provide the thrust, an RTG which will provide the energy at the front, and a dish to radio back to Earth. So this shows it arriving at Proxima b. This is Proxima Centauri here, our closest star, which is 4 light years away. So I think the mission could be launched by something like 2035, Proxima Centauri reached by 2045, and a signal received by Earth by 2049, if this was done. Okay. So I can now conclude. So Quantized inertia, the theory has been well tested on astronomical data. I've been testing it for 20 years. I've made many tests, even far more than I've even told you today. Been doing it over 20 years, and I've published 28 papers on it, and it's not failed so far. It's been a success. Tests have also now been done in the lab and in space. It represents a deeper, more predictive physics, I think. It explains inertia, and it's the kind of idea is that inertia is not an intrinsic thing which is stored in a mass, but it's something due to the interaction of that mass with the rest of the cosmos and the information it has about the cosmos. So quantized inertia will get rid of dark matter. It gets rid of the need for gravitational constant. And it also suggests that the universe is not actually expanding. But I haven't gone into that today, but it does. Quantized inertia enables satellite station keeping without fuel. So that would be much cheaper. And satellites would be much longer lived, saving a lot of money that way. I think it can produce quantum launch. So rockets would be obsolete, and launches will be much cheaper and safer and quieter. And I haven't discussed it today, but I think there's a way of getting energy from it as well, using a method similar to the capacitor. And I think we could produce an Oort Proxima mission that would take something like 10 or 15 years to get there with this method. Okay, so thanks for listening. I'll be happy to take questions, and I'd just like to point out I'm not at a university anymore. I'm a privately crowd-funded scientist. So if you want to support my work, please do so at Patreon, the address of which is shown here. And you can email me as well on this email address to ask questions. So thanks for listening.
Thanks, Dr. McCulloch. I know it's 1:30 in the morning your time, so we'll try not to keep you too long. But let's see if we have any questions.
Hi, Mike. Thank you for that wonderful presentation, which was an excellent follow-up on the first one you gave to us. When was that?
February 24.
So my question is actually kind of just for fun. If you had a probe accelerating from here to Proxima Centauri and making it there in 15 years, by that time, how fast would it be going? Would it be going, and how long would it actually be in that system?
Yes, I've modeled it. So it would accelerate halfway up to about half the speed of light, and then you'd reverse polarity and slow it down.
Oh, that would be great. So it would actually be in the system longer, or maybe even for a long time.
Yeah, that's right. So it could orbit and have a look around.
Thank you.
Hi, Tom Black here. I was wondering where you were talking about trying to narrow the separation on the capacitors, and I'm curious as to what developments has been with dielectrics and so on to allow you to get to even smaller separations. I think in the chart that you showed, you had about 6 millinewtons at the smallest separation. How far do you think you can take it with current technology?
Well, with what we have at the moment, we can get it down to about 8 micron. There are some materials that might do better. For example, mica is a very good dielectric. But the trouble is, as far as I know, you can't have layers less than about 20 micron. So, but if we could have narrower layers of mica, that would be a great one. And more recently, I've been thinking about different ways to do it. So instead of capacitors, you could have an annular Josephson junction.
Interesting.
where the electrons are jumping across the gap at a great speed.
Okay. Thank you.
Yeah, I've got a few questions. I gather you've had a couple of goes at the space thing. This latest one, OTP2, is still up there. The early one had some issues, I guess, which I don't think were associated with your drive. But
Right.
I guess the latest one, there's been, it's been slowly declining its orbit, and you use the, I guess, semi-major axis as your metric to try to figure out what the thrusts were. Do you consider the changing kind of scale of the Earth's atmosphere associated with solar activity when trying to figure that out, and more specifically, kind of what your drag coefficient of your satellite would be versus the other one that you used as a reference? I'm not familiar with the. You mentioned a reference satellite in a similar orbit.
That's right. The reference satellite is the same shape as far as I know.
Okay.
So it's a cube. They're both CubeSats launched by the same Falcon 9.
Okay.
And
they're maintaining similar orientations, I guess, because they're.
yeah, I haven't looked at the orientation actually, but I do look. I have collected data nearly every day.
Okay.
On both of them, and when there's a solar event, you can see the effect on both of them. They both drop much faster.
Okay. So kind of a follow-up on that, kind of taking it from OTP2 to an interstellar mission, there's an implied acceleration that you used to get to Proxima Centauri in 10 to 15 years. Do you recall what that was in terms of your acceleration to because I assume it's constant acceleration to the halfway point and then constant back.
Ooh.
And well, I don't want to put you on the spot too much, but I'm just trying to compare that to the accelerations that we've typically seen, let's say in OTP2, and get some sort of order of magnitude difference between the two.
Yeah, it's not. Yeah, it's something like half a meter per second for the.
Okay.
Yeah, it's about half a meter per second for the interstellar mission.
Okay.
And the way we did it in the interstellar probe was we stacked the capacitors because it enhances the thrust that way. So we just had about 100 capacitors stacked up.
So what provides the energy for those?
The RTG.
So it doesn't lose, I guess, very much energy using it. That's probably at most a few hundred watts or something like that. I know I'm in the weeds, but I'm kind of curious about this stuff.
Yeah, I think RTGs do decay over 10 years or so, but yeah, it might it might make it to Proxima.
Okay. All right.
Right behind you too, Carl.
That's okay.
You sure?
Yeah.
Any other questions?
TG is a radiothermal generator. What they.
Yeah. That's right.
How they power deep space probe.
Any other questions? Well, first, Mike, let me say thanks again very much. Mike was here in February of 2024. We asked him when he had some more stuff to come back again. I've been watching some of your YouTube videos and the blogs and the like, and some of his theories are not very well liked, let's say, because there's hundreds of billions of dollars of money being spent on trying to find dark matter, and Dr. McCulloch says you don't need it. So whoa, so that's not a good thing. But you also have to remember that back in the day when Einstein was when he proposed his theory of special relativity, it was also not very well accepted, and people were like, whoa, where'd you come up with this idea?
Galileo.
Yeah, yeah, that's right. But I heard the most interesting thing from one of our members about 2 weeks ago when I told them that you were going to be here, and they said, you know, I want to listen to this because it's kind of like the whole thing with Einstein. Wouldn't it be cool to be in the room when Dr. McCulloch is talking about this, and he's proven to be true, and we saw it at the earliest phase before everybody else was on board? Wouldn't that be neat, right? So again, thanks so much for doing this. We appreciate it. I know it's kind of late there, and I'll probably connect up with you again about a year and a half just to see what's going on and see if you might want to do it again.
Oh, that'd be great.
Yeah.
And thanks for my mug. I've got a mug.
Now, just so everybody's aware, I sent that 10 minutes ago, and quantized inertia. That's the power of QI.
We got two of them now.
Yeah. All right. Hey, thanks so much, Dr. McCulloch. Truly appreciate it. Thanks a lot.
You're welcome. Thank you.